Let us take a few steps into first principles modeling. As we have learned, first principles models involves the use of mass, energy, and momentum balances, the so-called conservation principles that are of importance to engineers, particularly chemical engineers. The second component of the first principles model is what are called the constitutive relationships. These are relationships that you will not get from mass, energy, or momentum balances, but the constitutive relationships are formed in order to connect the symbols or variables you see when we write the conservation equations. And these often come from empirical observations, somebody with a keen eye noting the relationships between certain variables and using them as part of the model. So the model is not complete without the incorporation of constitutive relationships. Mass, energy, and momentum balances form the backbone, but they do not complete the formation of a mathematical model. The constitutive relationships are key. We will look at it through several examples in the video segments that follow. Now, the key idea behind model, right, behind writing a mathematical model is that the accumulation within the system is equal to the imbalance between the input and the output. And to be a little more specific, because there could be consumption of things, there could be formation of things as well. So the accumulation is the imbalance between input and formation of a certain species or energy, for example, and then its dissipation by consumption or by leaving the system. So there are two words there with a negative sign. Both mean that the property that we are tracking in the mathematical model that either goes out of the system or it is consumed into something else. There are two terms with a positive sign. Basically, this input brings in that property into the system, and in the system, the property may be further generated because of formation of that. Let me look at it through an example. Let's say this is any system that we have. Let's assume in this particular case, we have a CSTR, a continuous stirred tank reactor, in which the reaction A going to B takes place. So what happens here is there is a feed stream that contains only A, right? So the feed stream is pure A. So this is what we will consider as input in the system, input to the system rather. Now the system, the reactor will also produce an output stream. The output is going to be B because A gets converted into B, and there could be some unreacted A. So mainly B and a little bit of A, right? So that is going to be coming in the output. Why does B come in the output? Because A goes to be inside the reactor. So within the reactor, A gets consumed. A will get consumed. If not fully, at least to a certain extent. And in the reactor, B gets formed. So there is formation of B. So if you write the equation for A, let's say you're tracking species A, it is going to come in the input. It is going to come in the consumption term. A is not formed within the reactor, so A will not be featured in the formation term. A will also feature in the output term because there could be some unreacted A that goes out. Now if you look at B, the species B, B does not feature in the input. So in the input it will be 0. But in the formation it will feature heavily because B is formed out of the chemical reaction. B will not feature in the consumption term because B is not consumed within the reactor. So B will not feature in the input term, it will not feature in the consumption term, but it will feature in the formation term and in the output term. Now beyond input, consumption, formation and output, in systems that are operating under dynamic conditions, that means not at steady state, but what we would call as unsteady state, or we will call them as dynamic state, that means things are changing with time, there could also be accumulation of things within the vessel. All right. So A can be accumulated in the system. B can also get accumulated in the system. That means not all the B that is formed will find its way in the outlet stream. Some B will remain in the system, hidden somewhere in the corner in the system, right? Somewhere in the system. Likewise, A can also, when it comes in, yes, it comes in as input, it is consumed, and some of the unreacted A goes out, but some of the unreacted A can stay within the reactor. So there could be an accumulation that's there. So this is true of any system, right? This is true not only for the reactor that we have talked about, it is true for other chemical engineering equipment, it is true for other systems. For example, um, you could write this equation for a city, right? You can treat the city as a living organism, and you can talk about the inputs that the city uses, the outputs that that city provides, right? And consumption within the system, creation of wealth in the system. So all of these things can be written for other macro systems as well, for cities, societies, etc. So we will look at this, in several examples to follow. We will look at mainly chemical engineering systems, but we will nevertheless look at it. Now, one word is the constitutive relationships or approximate statements, right? They don't come from conservation principles. They are just approximate statements and that is noted by people who have operated the system. All right. And basically, they link the variables that you see in the conservation laws. All right. So with the constitutive relationships being included in the model, only then the mathematical model is completed. So examples of constitutive relationships are equation of state like PV is equal to nRT. Ohm's law in electrical engineering, right? Voltage is equal to resistance multiplied by current. Another example of a constitutive relationship is the rate of the reaction, which is denoted as minus RA. This minus is because we tend to indicate that A is consumed in the reaction, right? So minus RA is equal to, let's say, KCA to the power of N in general, right? So we can write this. N is called the order of the reaction. So if you choose N is equal to 1, we get a first order reaction, or it's called first order kinetics, which means minus RA is equal to K times CA. The rate of the reaction is always expressed in moles of A per meter cube per minute. That's the units of the rate of the reaction. Now the concentration, right? CA is the concentration of A. So the concentration of A is always moles of A per meter cube. Now to match the dimensionality of the left and right hand sides, the units of K for a first order reaction is going to be 1 per minute. So this is another example of a constitutive relationship. You will not get this minus RA is equal to KCA to the power of N, or just KCA in the case of a first order reaction. You will never get it from conservation principles. But this fact will be used along with a conservation principle in order to complete the mathematical model. So that's the power of the constitutive relationships. They are very, very important. So in the several examples that follow, we will invoke this concept of what is written here as the key idea. That means input plus formation minus output minus consumption equals accumulation. And if you are looking at steady state operation of a system, the accumulation term will be equal to 0. There is nothing accumulated in the system if the system is at steady state. And therefore, we would just say input is equal to output if there is no consumption or formation, or we would say input plus formation is equal to output plus consumption, because at steady state, accumulation is equal to 0. We will touch upon all these ideas in a due course of time. Thank you.